welcome to today's lesson. Today we are going to be doing our first quick review number 1. Our learning objective for today is to review some basic set theory. Our language objective is to explain why set theory is important. So let's take a look at our thinking for today. Let's take a look at our thinking question for today, and we are talking about sets. So what is a set? A set is a collection of numbers or objects. Each object is called an element or a member of the set. For our first example, we are going to be converting the following into symbolic mathematical language. So let's look at the first one here. It says X is an element of set A. So in math, we are going to start with X is an element, looks like a E, of our set A. Second one, Y is not an element of set B. So very similar. We're going to start with our set Y. We're going to represent our element, but this time we're saying is not, which means we're just going to cross it out, of our set B. P is a subset of Q. P is a subset of Q. So we start with our set P is a subset, a little C with a line under it, of set Q. X is a proper subset of Y. We start with X is a proper subset, just a little C, of set Y. And we have the empty set or null set. You could represent it as curly brace with nothing inside, or you can do a circle and a slash. But you can never combine those two together. So you can never ever do this. Do not do that. That's something that I tend to see people do. Sometimes they mesh them together, but it's not proper notation. All right, so that's some of our basics as far as our mathematical notation for sets. For the next piece here, two sets are equal if they have exactly the same elements in them. So if I have a set A, which contains the elements, let's say 1, 2, and 3, and we have a set B, if they are equal, set B should also contain 1, 2, and 3. That makes them equal. Set A equals set B. Compare and contrast. What's the difference between subset and proper subset? So P is a subset of Q if every element of P is also an element of Q. So that's very similar to the first piece I have here, but I'm going to draw this out. So let's say I have a set Q. P is a subset of set Q. If P is a subset of Q, that means that every element in P will also be an element of Q. Every single piece in set P, whatever members are in that set P, will also be members in set Q. P is a proper subset of Q if it's a subset of Q but is not equal to Q. So let's see if I could draw this out. Set Q, we have P is a proper subset, but P is not equal to Q. Again, this makes sense. They do share some of the same elements, but Q might have more elements. So if I'm thinking of this in terms of numbers, let's say set P contains the numbers 1, 2, and 3. Set Q will also contain those numbers plus more. It might have a 4, 5, 6. meaning that P and Q are not equal. They don't have the same exact elements within them. All right, let's use that knowledge of subsets and proper subsets to answer questions from example 2. So here we're going to determine if the following are sometimes, always, or never true. So let's start with number 1. It says when X is an element of set A and A is a subset of set B, that means that X is an element of B. So I'm going to draw this out just to visualize this. It says when X is an element of set A and A is a subset of B, which means that we have some set B and A is a little member in there, then X is also an element of B. All right, so I have in set A, we have a member called X. And is that member also part of B? Yes, it is. Why? Because of this piece here. If I have a subset, then every member in that small set is also going to be a member of the big set. So this is always true. It's always true based on our definition. For number 2, when A is a proper subset of B, A and B are equal sets. So we have A is a proper subset of B. We have B, we have A here. A and B are equal sets. Impossible. That goes back to our definition of proper subset. So this is never true. Set A and set B are definitely not equal sets. Last one. For number 3, when X is an element of B and A is a subset of B, X is an element of A. So let me draw this out again. We have when X is an element of B and A is a subset of B. So we have A is a subset of B, and they're telling me that X is a member of set B. Does that mean that X is also in A? Maybe, maybe not. So this can be sometimes true. Let's go to more on sets. So more on sets. Definition. The intersection of sets A and B is the element of which are both in A and B. So intersection. We are going to represent the intersection. We have A intersection B. If I am representing this using a Venn diagram, we have two sets. Call this set A, set B. The intersection is what they both have in common, which would be this piece here. This is A intersection B. Next, two sets A and B are disjoint or mutually exclusive if they have no members in common. So how do we represent this mathematically? We will write, we have that here that there are no members in common, no elements in common. And if I'm representing that in a Venn diagram, we have our two sets, A, set B, but there's nothing in common. So they are disjoint or mutually exclusive. The union. The union of sets A and B is the elements which are either in A or B. So our union symbol, A union B, we have our sets, set A, set B. The union is going to be all of this outside piece minus the inner piece. So it could be in set A elements in set A or elements from set B. That's our union. The universal set. The universal set U is the set under consideration. So as far as this goes, there is no symbol for that. So I'm just gonna cross this out. And if I am drawing a Venn diagram of our universe, this is our main set. Most often when we draw Venn diagrams, we do have this universal set. So we are always dealing with some universe we're living on to make it more accurate, right? So there's our universal set. The last one here is the complement of set A is the set of all elements of U which are not in set A. So we have the complement. We tend to write, let's say, our set, this little apostrophe. We have our universe, set U. We have our set A. And the complement of set A is pretty much everything that is not in that A, which would be, in this case, the outside piece. So now that we have an idea of what sets are, we're going to look at some of our famous sets. You have been dealing with sets of numbers for a very, very long time. So let us look at the last piece here. We have the natural numbers. Now, natural numbers, when I remember, or the way I remember this is I deal with how we learn to count. So when we go to school, when you are learning to count objects, you always start with 1. We count 1, 2, 3, 4, 5, and so forth. So the natural numbers are pretty much just that. The symbol for the natural numbers, which we should all know, the double N. Now, our definition would be the numbers itself. So we are dealing with numbers 1, 2, 3, go on forever. That's the set. I left the space here because in IB, the natural numbers actually also involves 0. This is very important for IB. Include 0. This is only because we are in the IB course. The integers. The integers are the next types of numbers you tend to learn about. So this is usually around 6th grade, you start learning about integers, positive and negative numbers. The symbol for integers is this Z. You are dealing with all numbers that are in the naturals, but you are taking into account that every single number has a positive and a negative. Positive integers. So if I'm dealing with the positive integers, the symbol would be very similar to that one, double Z, but with a little plus. And we will be dealing with numbers 1, 2, 3, so forth. So the reason that IB includes 0 in the natural numbers is because of this. We tend to define the positive integers as numbers 1 all the way to infinity. So they included the 0 in the natural numbers. All right, rational numbers. Rationals are all our fractions. So the rationals are represented with this Q. We are dealing with some sort of fractions, P over Q, where P and Q are elements in the set of integers, right? You could have positive, negative, fractions, and so forth. And then we are finally up to the reals, the set of reals, double R, which would be all numbers on the number line, on the number. So every single number that I can place on a number line. Example 3. Create a Venn diagram representing the natural numbers, integers, rationals, and reals. Include example elements in each region. All right, so let's start with the innermost set, I'm thinking of when I learned to count. So when I learned to count, I learned the natural numbers first, dealing with 0, 1, 2, and so forth. As I got older and more mathematically aware of numbers, we went into the integers. So we have some positive values, negative values. Then I got more mathematically aware of my numbers, the rationals. But let's see, 2/3. Any number will do, right? Positive or negative. And we make it to the set of reals. The set of reals has all those numbers plus more. So numbers like radicals, numbers like our famous pi, and so many more. So if I'm creating a Venn diagram, we're living in some universe of numbers where my subsets are the naturals, the integers, the rationals, and we are in the set of reals. All right, so hopefully this was a nice little recap on set notation. See you in our next video.